Audio Jungle. Audio Jungle.
Rocket performance, rocket performance parameters. Okay, now what are the parameters? So first one is nothing but total impulse. Total impulse. Second one is a specific impulse. Third one is nothing but propellant consumptions. Okay. Fourth one is thrust coefficient. And the last, which is very important, and many times get question they have asked for the characteristics velocity. Characteristics velocity. So these are the rocket performance parameter, and all are very important. Question they are asking basically in GATE aerospace, question they are asking from here only. All right. So one by one, patiently we'll see this and formulation, single line definition and formula directly I'm going to give here. Okay. 1, 2, 3, 4 and 5. All right. Number one. Number one is nothing but total impulse. Total impulse. So this total impulse is, first of all, impulse is denoted by I, and here I said total impulse, so I T. I T. All right. So what is the impulse? So impulse is nothing but it's imparted due to this change in momentum over a certain period of time. Okay. In other words, you can say impulse imparted to the vehicle during its acceleration. Okay. And if you write the formula for the impulse, then I must say impulse is imparted due to this change in momentum over certain period of time. Okay. So basically if I say impulse, total impulse, so total impulse will be whatever the force and for what time it is imparted to the body or imparted to the system, force into that instantaneous time. Instantaneous time, the meaning is for what short time or period that force is what acting over the body, that force into time will give the impulse. So I have here given the integration. If I'm integrating this from initial time, which is 0 to burning time, TB. TB is the burning time of the propellant into force into time dt. So this is nothing but total impulse. Okay. So total impulse is the IT 0 to TB, burning time of the propellant. It is nothing but F into dt. So need to remember this formula. Okay. Now here whatever the formula you have for the total impulse IT 0 to TB F into dt. What is the TB? It's a burning time of propellant. Okay. And obviously it is burning, so thrust will be produced. So this is nothing but thrust produced. Okay. And dt is nothing but obviously instantaneous time. So this formula will be IT is equal to 0 to TB F into dt, 0 to TB if I am writing. Then what is the thrust force? So thrust force is nothing but mass flow rate of the propellant. We had seen in previous lectures. If you go and check what is the thrust produced by the rocket engine, F, which is nothing but m dot p into effective equivalent velocity, m dot p into v equivalent, and as dt will be as usual. All right. So now if we check, this is nothing but m dot p into v equivalent and dt. If you integrate it, then what you will get? Dt will be t, and limit if you put, then it is tb. So now what is the total impulse? You can say it is equal to m dot p v equivalent into tb. tb is the burning time of the propellant. Okay, this is the formula. Or again, this formula you can write it is equal to m dot p. You can write mp, which is the mass of the propellant, divided by total burning time of the propellant, because it is m dot. M dot means flow rate. So I am writing here mp divided by t. Mp divided by t is nothing but m dot p. It is very usual. No? So instead of m dot p, I am writing mp by tb. Okay, tb is the burning time, total burning time of the propellant, into v equivalent into tb. So this value will be cancel out tb. What you will get? mp into v equivalent. So finally what we got? it is the total impulse. Now in different format you have, it is nothing but finally this is mp into B. This is the final formula. Okay. So what happened many times, student in flow they will commit mistake here. What mistake? Because the practice is what always write to write practice is to write always m dot p. So they will remember m dot p into V equivalent. Remember, if you are writing m dot p V equivalent, then it will not be a total impulse. It will be thrust. The biggest difference between the formula, if you are writing, listen again, if you are writing m dot p into V equivalent, then this will not be IT, this will be thrust. So please, you just mark there, so that when you mug up the formula, that time you should very clear. If you are writing m dot p into V equivalent, so it will be thrust force. But if you are writing MP into V equivalent, then it will be total impulse. What is this? Sorry, what is this m dot p? M dot p is the mass of propellant. Okay, and unit will be in kg. What is this m dot p? Mass flow rate of propellant kg per second. M dot p kg per second, m dot mp, which is kg. So that is very basic thing, but you need to remember. Okay, all right. Now, so this is the first performance parameter of the rocket. Now second, we'll go for the this. So we'll go for the second parameter. What is the second parameter? Second parameter is the, I think, specific impulse, right? Second parameter is the specific impulse. Okay. So specific so what is the specific impulse? So specific impulse, in single line you need to write the definition. The specific impulse, it is defined impulse per unit. It is impulse per unit weight of the propellant. Okay. So if you say this is what propellant. Okay. Now for this, suppose it is in casing. Okay. So now for this, whatever the mass, because once it is started burning, so whatever the mass for this propellant, it is nothing but m dot p, mass flow rate. No? And what is the mass? It is mp. So impulse per unit weight of the propellant, and what is the weight for this? It is mp into g. That is the weight. No? You can write this is mass flow rate. This is mass. This is weight. Okay. So what is the impulse? Specific impulse. Specific impulse, it is denoted by ISP. Okay, it is denoted by ISP, and it is nothing but impulse per unit weight. What impulse? Total impulse. So in practice, total impulse, you can write IT or only I divided by weight of the propellant. What is the weight of the propellant? It is WP, and I divided by What is the WP? It is MP into G. All right, MP into G. Now here you can check this ISP is nothing but I divided by WP, or what is the value of I? Just now you have seen I is nothing but, that is total impulse, and it is nothing but MP into V equivalent. So you can write here MP into V equivalent divided by MP into G. So it is nothing but V equivalent by G. This formula you need to remember. So you need to check in problem once you will go and solve the problem. That time you need to check what value they have given. Based on that you use. If they have given weight of the propellant and total impulse, suppose they have given, then use the formula I upon WP. If they have given equivalent velocity, then you can use this formula also. Yes or no? Fine. All right. So this is the formula. I is total impulse, okay, and MP is the total mass expelled propellant. So all the notation is what basic only, like what I have repeated many times. So I'm not going to write every time what is V equivalent, what is MP, what is I. It is now in starting only I had explained. So you need to consider that, because every time writing the same thing not good. So fine. Now this formula also you can write in terms of the thrust. Suppose they have given thrust and they are asking specific impulse, then what you will do? So we need to relate in that way also. So again I will write this impulse formula, this specific impulse formula. So I will write here, it is nothing but ISP. Check what is the first formula here you have seen. The first formula you have seen, it is I divided by WP. I divided by WP, weight of the propellant, okay, is equal to, then what you have seen? You have seen it is nothing but V equivalent by Z, okay, V equivalent by G. Now what is the V equivalent relation between thrust force? No? Check what is the thrust force here. Here I have written what is the V equivalent here. Check V equivalent divided is equal to F, which is nothing but thrust force divided by m dot P. So I can write V equivalent is nothing but thrust force divided by m dot P into G. This is nothing but F. F is thrust force, okay, or whatever notation you can take, thrust divided by m dot P is nothing but weight W dot P. There should not be any confusion. Okay, what is W dot P? That should be very clear. Huh? This is the final formula of the specific impulse. Okay, I will write. Effective exhaust velocity F, which is also T, is nothing but thrust. WP is weight of propellant, and W dot P, it is weight flow rate of propellant. W dot P and W. Here it is very important. Okay, there should not be any confusion. You are writing WP, it means total impulse in numerator. If you are writing W dot P, it means in numerator it is thrust. Okay. So basically ISP you can see here. ISP also can define as thrust per unit weight flow rate. Thrust per unit weight flow rate consumptions of propellant. Okay. Always remember ISP does not depend on the flight velocity. Does not depend on the flight velocity. Okay. Specific impulse ISP represents the time average specific impulse over entire period of operation of rocket engine. Okay. The value of specific impulse does vary during transient operation. Okay, namely start or shutdown period. So the total dependency of the ISP, if you check, it is depending on the parameters which is already here written. So sometimes theory question also they are asking like what is the dependency of ISP, so you can answer for that. And very frequent question they had asked many times and asked in previous and nowadays also they are asking ISP value. They will say for solid rocket what is the range of ISP or what is the value. Simple, they will give the ISP value and they will say what type of engine has been used, or the different engines they will give and they will say like okay what is the ISP for this engine. So I will give one table. In that table, solid, liquid, hybrid, solar, nuclear, electrical rocket engine, which is also called arc heating rocket engine. For that, I will give ISP range. You need to remember this value, okay? And it is very frequent they are asking in competition. So now we just draw this table. Rocket engines, and this side we have specific impulse. Okay, so now we have first solid rocket engine, solid rocket engines and यार छोड़ो HPREs. Okay, nice score. यार मैं देखने लग गया HPREs ना. Then liquid rocket engines. Okay, LPREs. Then hybrid engines, HPREs, then solar rocket engine, then we have a nuclear, and then electrical, or it is also called arc heating. So for each and every one will have their special ISP value, and they are asking value, okay, in examination. This is 400 to 2000, 600 to 1000, 400 to 700, hybrid 300 to 500, 300 to 460, 310. All right, so now we have impulse to weight ratio of rocket system. So these are the small topics, okay? I mean one-liner things, but we need to know that. So it is defined as total impulse to initial vehicle weight, okay? So if I say initial vehicle weight, that means that rocket is what now going to lift off. So that propellant of the rocket, you can say it is going to start burning now. It is not yet started, yes or no? So in that case you have to take this is the exit. We have a propellant here, this is the propellant, you can see, okay, here. All right, now so three things we have, okay? This is the, here suppose this is the payload, so mass of payload, mass of payload will be denoted by ml. This is what mass of propellant, it will be denoted by MP. Okay, and you can say that structural mass of the vehicle, mass of the vehicle, it will be denoted by ms. Okay, so what is the total initial weight then? Total initial weight of rocket, it will be denoted by m naught. Okay, so what is the m naught? M naught is nothing but, you check, it is first start from the top, it is ml, which is the mass of the payload. Okay, then mass of the propellant mp plus mass of the structure. Okay, need to remember this because now we are moving towards numerical part. So this all points what I'm going to mark here, it is very important and it is the foundation of the numerical. Once you understood basic thing, then definitely you will able to understand numerical part very easy. Okay, in very easy way you will understand, otherwise there will be lots of confusion in the rocket problems. So initial to weight ratio of rocket system, sorry, impulse to weight ratio of rocket system. So what is the impulse to weight ratio? Impulse to weight ratio is nothing but I by W. Okay, and it is I is nothing but that is the uh, total impulse. So I must say it is IT, total impulse divided by total weight, and this weight is nothing but initial vehicle weight. So what is the initial vehicle weight? I can write W naught. So IT we know it is nothing but ISP into G. Okay, sorry, it is not ISP into G, it is, let me write this, ISP into mass of the propellant. Check it, total impulse I am saying. So see, ISP into mass of propellant divided by W naught is nothing but mass of the payload plus mass of the propellant plus mass of the structure. Okay, and it is G. All right, so this formula is what very important. This is called impulse to weight ratio. Okay, so I'll put in box. So sometimes they will give to you impulse to weight ratio. So you should know what is the mean of initial weight. Initial weight means that burning is what just started. It is not completed. If burning is what completed, then MP will be, mass of the propellant will be 0, because propellant is what burning is what completed, then mass of the propellant will be 0. But here I am saying initial weight of the rocket system, it means that mass of the propellant is still there, it is not completely burnt, it is just going to start burning process and all. Okay, number one, this is the point one. All the articles what I am writing here, it is based on numerical. Okay, numerical they are asking based on this parameters what I am writing here. So second parameters we have, it is called mass ratio. So these are the terminology they are using in the numerical part. Okay, that directly they will say, okay, mass ratio is this. If they said mass ratio, then what you will understand? For that reason, it is required to go with this theory part. Okay, one-liner theory we have, mass ratio. Okay, mass ratio, MR. What is the mass ratio? So mass ratio is nothing but, the mass ratio is defined as the final mass. Okay, it is the ratio of, in short I am writing, okay, it is the ratio of final mass if I say final mass after rocket operation, if I say it is the ratio of final mass after rocket operation, so what is the mean of it? After rocket operation, so definitely if I say after rocket operation, it means whatever the amount of the propellants, it is completely consumed, or it is completely burned, you can say, or it is consumed. So in bracket also required to write or after propellant were consumed, bracket, yeah? to the initial mass, to the initial mass m naught, to the initial mass before rocket operation, before. Okay, so this term you need to remember. So what is the MR? MR is the mass ratio, and it is denoted by M small f divided by m naught. What is the MF? MF is the final mass after rocket operation divided by initial mass before rocket operation. So this ratio is very useful, you need to remember. Okay, this ratio is very useful. Whatever the ratio I am writing here, you please remember, okay, because I will use each and every ratios here in further points. Okay, so this is the second points. What is the third points? So it is nothing but propellant mass fraction. Propellant mass fraction, it is denoted by xi, or in somewhere it is called as zeta, xi or zeta, whatever you want to take, you can take for the notation. Okay, it is denoted by, here I am just writing zeta I have written. So what is the propellant mass fraction? So it is defined as the ratio of propellant mass MP to the initial mass. What is the initial mass? M naught, in bracket I can write, and propellant mass is what? MP. Okay, so what is the zeta? Zeta is nothing but mass of the propellant divided by mass of initial mass of the system. What is the mass of the propellant? Here you check, you can check. So mass of the propellant, if you check what is the mass of the propellant, so mass of the propellant MP will be what? M naught minus in bracket ML and MS. Yes or no? Or in other word, what you can say, it is MF. MF is what? MF is the final mass after rocket operation. So even though after rocket operation we will have a mass of the payload and mass of the structure, yes or no? We are considering that payload is what? Not launched. You just say it is only, we are talking about the, otherwise you may think like, okay, after rocket operation means what? Whatever the payload we are having, like satellite or anything, we have launched. No, I mean we have pushed it into orbits and all. No, don't think in that way. You just think like, okay, if rocket operation before
mass of the rocket before operation and after operation, so it is related to the mass of propellant. If I say before rocket operation, it means mass of propellant is what is still there, it is not completely consumed. If I say after mass of the system after operation, so it means after operation, it means that mass of the propellant is what completely consumed. That's the mean of it. Okay, so MP will be 0 that time. Now, so here if you want to write the mass of the propellant, so mass of the propellant, you can say what is the initial mass m naught minus final, okay, minus final divided by initial mass m naught, okay. And this is also, you can say, if you go for this m naught minus mf, what is the initial mass m naught? So initial mass m naught, you can say mass of the propellant, because you are talking initial, so m naught will be the mass of the propellant, because initially propellant will be there, plus mf, okay. So, and in, or you can say m naught is nothing but, if you want to write complete, you can write m naught minus mf. What is the initial mass? Initial mass is nothing but mass of propellant plus mass of the payload plus mass of the structure. The full length also you can write, otherwise mp plus mf you can write. Yes or no? Because if you see what is the m naught initial mass, or what is the, if I say what is the minus, what is the final mass, so you can say final mass is nothing but initial mass minus mass of the propellant, because this mass of propellant will be that part will be deducted. Why it is deducted? Because you are talking about final mass, and final mass means what is the mass of the rocket system after operation. So after operation, this mass of the propellant will be removed, because it is now completely consumed. So you need to remember this final mass is nothing but always initial mass minus mass of the propellant. So somewhere if it is written m naught, so what is the mean of m naught? M naught is nothing but mf plus mp. So this part here I have written this. Or this initial mass also, you know very well, it is nothing but mass of the payload plus mass of the propellant plus mass of the structure. This is also, because m naught here itself you have seen first, this m naught. What is the m naught? ml plus mp plus ms. So the same thing I have written here also. Okay, so this thing is need to careful, otherwise so much confusion while you are solving numericals, so much confusion you may get. So each and every lines you need to understand. Okay, now so another format also you can have, because this is numerical point of view very important, this mass fraction, propellant mass fraction. So what I told you, mass propellant mass fraction is nothing but mass of the propellant mp divided by mass of the initial mass of the system. So initial mass you can write m naught, yes or no? And you have seen this mp is nothing but, what is the mp? Mp is nothing but m naught minus mf. So it is m naught minus mf divided by m naught. You have written this is here, this part. Okay, now here only you can break again. So again one more formula you will get. You will have m naught by m naught separately, you have taken this, and if we check, it is nothing but 1 minus mf by m naught. So zeta is nothing but 1 minus final mass by initial mass. Check what is the final mass by initial mass. Mf by m naught is nothing but mr, which is called mass ratio. So this is 1 minus mr. This is very important. Okay, this is very important result, and it is very useful for the numerical, and numerical based on this they are 100% they are asking for one day exam. If you go separate even exam for ISRO or HL, then you may get numerical based on these formulas. I mean, whatever today I am explaining, it is very important, okay, for all exams. So zeta is nothing but 1 minus mr, where zeta is nothing but propellant mass fraction, and mr is the mass ratio. Okay, so now you can get here like mr is always less than 1, yes or no? Mr is always less than 1. Mr is less than 1. Why it is? Because m naught is always greater than mf. What is the m naught? It is before operation. So if before operation, definitely mass will be more, because propellant mass is still there, but mf is after burning. So it is very important. Okay, mr is always less than 1, because you can draw the plot also. Plot is not required, but you can draw if you want. So this is the propellant mass fraction, and it is always greater than 1. Okay, always greater than 1. Greater than 1 in the sense, not greater than 1, you can say it is positive value, or you just remove this part. But that based on consumption of mr, you can draw a zeta also. You are not going to draw plot, so it is not required. Just I was saying, like, if you want to draw the plot, then zeta based on mr variation, because 1 is constant. So once mr is what changing, then zeta will be changing, so you can draw the plot also. So for one day exam, definitely graph based question will not come, but in semester and all, you might have solved in your during your BTech course, based on the plot you had solved the numerical. So here it is not required actually that. Anyway, now this is what propellant mass fraction. Now we'll go for the next, which is nothing but this is the one problem we need to solve here, and then we'll go for the next topic. So we have problem based on this performance parameter. So this is what problem number 1. Okay. Now a rocket engine with chamber pressure of 4.5 megapascal and nozzle throat diameter of 110 mm produces thrust of 17 kilonewton by consuming propellant flowrate of 7.5 kg per second with calorific value of 25 megajoule per kg if the flight velocity happens to be 850 meter per second. 850 meter per second. Determine number 1, specific impulse. Number 2, effective exhaust velocity. Number 3, specific propellant consumption. And point 4 is thrust power. Point 5 is thrust coefficient, and you know it is denoted by ISP, effective exhaust velocity, SPC, thrust power, TP, and CF. Thrust power also you can say FP if you want, it's your choice. Check here. So 4.5 megapascal, this is what given. Chamber pressure is what, 4.5 megapascal. Throat diameter you can say DTH, how much, 110 mm, 110 mm. Produces that thrust they have given to us, it is 17 kilonewton, and mass of the propellant m dot p is given, sorry, 7.5, not 17, it's a 7.5. kg per second. Okay, calorific value means here they have given a CV they have given to us, CV, that is the calorific value, which is nothing but 25 megajoule kg, and last is the flight velocity they have given to us, it is how much, at 50 meter per second. Okay, so now solution for this problem is simple one. Number 1, what is the number 1? It is specific impulse. What is the formula for this? It is ISP. What is the ISP? It is thrust F divided by m dot p into g. What is the thrust? It is given 17 kilonewtons, so 17 into 10 power 3. M dot p, mass flow rate of the propellant, it is given 7.5. G they have not given, but you can consider 9.81. Okay, if you solve this, then approximate you will get, as you have calculated, 231.06 second. So this is the ISP. This is number 1. All right, now we'll go for the number 2. What is the number 2? Number 2 is nothing but effective exhaust velocity. Okay, so what is the effective exhaust velocity? As you know, it is nothing but ISP by G. You check that formula ISP, that one box I had given, and in the box many formulas was there. So there I had given ISP is equal to V equivalent or effective velocity into G. ISP is equal to V effective into G. So what is V effective? It is ISP by G. What is the ISP? Just now you have calculated 231.06 divided by G is nothing but 9.8. Now if you oh, what formula I had taken? Wait, this value V effect is so much. This formula is what? ISPG is equal to V effective by Z. If you remember, no, I made mistake. Sorry. Now correct this. So actually, I think little bit hurry. I don't know why. ISPG. If you remember, we had proved that it is V effective into G. All right. So what is the V effective by Z? Now it is correct. It was V effective. It was proved V effective by G. If you remember. So what is V effective now? V effective is nothing but ISP into G. So what is the ISP? You have calculated 231.06 what I remember into 9.8. If you do this calculation, so here approximate you will get 2266.7 meter per second. This is the value. Please check the value of this formula. If you remember, we had proved ISP is equal to, we had proved this, it was F dot F is F divided by M dot PG. If you check F divided by M dot into Z, what is the F? F is nothing but V equivalent or effective into M dot P divided by M dot P into G. M dot P cancel out. So what you will have? You will have ISP is equal to V effective by G. So you use that formula, okay? So it is very tough for me to remember the formula, but anyway. Alright, so this second value you have calculated. Now we'll go for the third value. What is the third value? Third value we have a specific propellant consumption. It is nothing but SPC. Okay. What is the SPC? SPC is nothing but, I had given one formula and it was very large in box. Many formulas I had given for SPC, but finally if you remember it was 1 upon ISP. What is the ISP here? It is given 231, I think. 231.06. If you solve this, what you will get? You will get 0.0043 kg per Newton second. This is number 3. Okay, we'll go for number 4. What is the number 4? Thrust power. Thrust power. Okay, what is the thrust power? It is FP. What is the formula? Thrust power is nothing but, power is what? Force into area. What is the force? Force into velocity. What is the force? Thrust. Force into velocity. What is the thrust you have here? 17 kilonewton. So 17 into 10 power 3. And velocity of the vehicle they have given to us how much? It is here it is given 850 meter per second. 850. If you solve this, then approximately you will get 14.4, because it is power, so it is watt. So what is the thrust power? It is nothing but 14.45 megawatt. This is number 4. Now we'll go for number 5. So what is the number 5? Number 5 is thrust coefficient. what is the thrust coefficient? It is CF. By formula we know CF is nothing but thrust force divided by PC into ATH, throat area. What is the thrust force? It is, I think, 17 kilonewton they have given to us. Check 17 into 10 power 3 divided by PC. If I am not wrong, it was 4.5 mega bar. Check it. 4.5 megapascal. Sorry, megapascal they have given. And diameter mm it is given 110. So 110 they have given diameter. Now so we'll write 4.5 megapascal, so 10 power 6 into area is nothing but 5 by 4 into diameter 110. So 110 you convert it into meter, so it is 0.11 5 by 4 d square. If you solve this, 0.3975. One more you can add here in problem itself. 6 number. 6 is very interesting actually. It is C star. Okay, we need to find C star, 6 number. What is the 6? Characteristics velocity. C star we need to calculate. Add that. So 6 number is nothing but characteristics velocity. What is this? It is C star. Check as per given data what we have find yet. So what is the C star? Many formulas I told you yesterday. I had given all the parameters. These parameters, 6 parameters you have calculated, and all 6 parameters I had explained in my last lecture. So if you check there, C star in different format it was given in different term. So one it was V effective divided by CF. If you check this formula is available or not, this one you can use because V effective you have and CF you have. What is the V effective? V effective you have 2266.7. So it is 2266.7 divided by it is nothing but 0.3975. If you solve this, then you will get how much? So it is 5698 meter per second. Done. So if you go for the efficiencies, so we have a 2 efficiencies, okay, and it is nothing but thermal efficiency and propulsion efficiency. It is denoted by eta P and it is denoted by eta TH. So in similar way what you had seen for the jet propulsion, same way we can write efficiency formula for the rocket propulsion. So here I am just going to write directly this formula, eta TH. It is nothing but V equivalent square plus V square divided by 2 combustion chamber efficiency into heat value. Okay. One more thing I just want to add here. This thermal efficiency is basically in word. It is nothing but formula I will write. Engine power output. Okay. Engine power output divided by available chemical power developed by combustion. So in word also now you have formula, how it comes, how this formula comes. This engine power output is nothing but 1 by 2 m dot p v equivalent square plus v square divided by that available chemical power, it is nothing but eta cc into m dot p. All formulas you are now aware with this, like what is the eta cc m dot phv, you know, in combustion chamber you had seen that available chemical energy. I had written many times that available chemical energy in combustion chamber. So eta cc, in jet propulsion it was m dot f into hp, but it is rocket propulsion, so m dot p, for mass flow rate of the propellant. Rest everything is what same, so it is v equivalent square plus v square divided by 2 times eta cc m dot p into h. All right, so this formula you need to remember. So how it comes, that also I have in 2 lines explained, so at least this will be clear in your mind. Okay, sometimes source is required to know actually. Okay, so what is the source? That source you should know. In between steps you can remove, no problem, but at least source you should know. So what is the source? This is the source. All right, fine. This is what thermal efficiency. In the same way we can go for the propulsive efficiency. So point 2, propulsive efficiency. So just like in jet propulsion we had seen propulsive efficiency, we have propulsive efficiency for the rocket propulsion also, rocket system. So first I will write in word. So eta p is nothing but, it is propulsion power or thrust power based. I will write thrust power. Thrust power divided by engine output power. Engine output power. Thrust power divided by engine output power. So if you solve this, so final formula I am just going to write. Okay, after getting all the manipulation, 2-3 steps you have. So this formula will be 2 into v divided by v equivalent divided by 1 plus v upon v equivalent square. See, in similar way you had seen for the jet propulsion also, there was some different thing, but similar way we had seen in jet propulsion also. So it is eta p. In jet propulsion this square was not there, rest everything is what same. So it is nothing but 2 into sigma divided by 1 plus sigma square. In jet propulsion it was 2 alpha divided by 1 plus alpha. What is the sigma? It is nothing but speed ratio. This is called propulsive efficiency. This is called propulsive. What is the sigma then? Sigma is nothing but v upon v equivalent. It is called speed ratio. That's all. Done. Okay, you need to remember. So this is the propulsive efficiency. All right. Overall efficiency, obviously thermal efficiency into propulsive efficiency will give the overall efficiency. Done. So all right, so now this is the problem number 2, and this type of question they are asking in exam. Okay, one question will be like this and another question will be related to multi-staging. 2-3 questions they are asking every year. Okay, in GATE Aerospace. So problem number 2. All right. So it's a simple one. A rocket having an effective jet velocity of 1100 meter per second and flying at 8500 kmph kilometer per hour has propellant flow rate has propellant flow rate of 6 kg per second. If the heat or if the calorific value of propellant is 43 megajoule, find number 1 eta P propulsive efficiency, eta TS thermal efficiency, eta E overall efficiency. So efficiencies are the part of your GATE syllabus or not, but rocket propulsion is the subject, so each and every topics they will not mention in syllabus, so you need to consider, okay, efficiency they can ask to your exam, in your exam, okay. You cannot say like, okay, efficiency that is not in your syllabus, because as I told you, it is the part of that rocket calculation, okay. So you need to find this. So now what are the given data here? Need to check. Given what they have given, V effective or V equivalent is nothing but 1100 meter per second, and the vehicle velocity is nothing but 8500 kmph. If you convert it into meter per second, so you will get 236.11 meter per second. Okay, mass of the propellant here, it is given how much? 6 kg per second, and heat value for the propellant they have given, it is 43 megajoule per kg. Now for this problem directly we can calculate first eta P. So I have directly given the formula for eta P. So what is the formula? It is 2 sigma divided by 1 plus sigma square, 2 into, what is the formula of it? That formula I have given here, see, it is V upon V equivalent or effective, right? So V upon V equivalent divided by 1 plus V upon V equivalent. So everything you have here, 2 into, what is the V? V is nothing but 236 divided by 1100, 1 plus divided by 1100. Find it. .66%, because by default propulsion efficiency is what in percentage, so I am writing it into that. This is the first one. Second one is what? It's a thermal efficiency. So what is the thermal efficiency? 0.2. You have written the formula thermal efficiency. It is V effective square plus V square divided by 2 eta Cc m dot P HV. So I will write here V equivalent square plus vehicle square 2 into eta Cc chamber combustion chamber efficiency HV into mass of the propellant. So if you check here, V effective equivalent, it is given I think 1100 plus flight vehicle speed is 236.11 divided by 2. Combustion chamber efficiency they have not given, so you consider 100%, so it is 1. Heat value I think it is 43 megajoule, no? Megajoule. So 43 and for 6 into mass of the propellant, I think it is 6 kg per second. So if you calculate this thermal efficiency, so yes, this one is approximate 7.89%. Fine. What is the third one? Eta O. So as I explained in jet propulsion also, eta O is nothing but thermal efficiency into propulsion efficiency. Propulsive efficiency. What is the thermal efficiency? 7.89. So you can write 0.00 not 00 0.0789 into what is the propulsion efficiency? It is 0.766, no? 0.766. If you do this overall efficiency approximate, you will get, and calculate this value, how much it is? 0.0789 into 0.766, so it is 0.00 sorry 0.06043, but in percentage it is nothing but multiply by 100, so you will get 6 point something. This is the propulsion efficiency, sorry, overall efficiency. Alright, this is the overall efficiency. Nice. Done.